In the depths of Bikini Bottom, SpongeBob faces a new underwater crisis. He must learn to protect our water bodies from the effects of pollutants. What's his secret formula? Introducing the Advection-Dispersion equation. Built upon by various researchers over time, this fundamental equation in fluid dynamics is used by environmental and hydraulic civil engineers to study the movement of solutes such as harmful pollutants in fluids. Are you ready, kids? Let's discuss. Advection is the movement of solute due to the movement of the fluid. Imagine particles in a river flow. Their movement is due to the flow of the river itself. In calculus, the first derivative of the solute concentration with respect to position and time multiplied by the velocity gives us advection. On the other hand, dispersion is spreading out because of molecular diffusion and changes in flow velocities. If we take the second derivative of the concentration and multiply it by the dispersion coefficient, we obtain our dispersion. These combined effects of flow make it hard for us to remediate the spread of contaminants in our groundwater, surface water, or even in the atmosphere. With the use of ADE, we are not only able to determine the concentration of contaminants, but their location and possible next routes. This is what differs it from the law of conservation of mass. They both model mass transport, but the LOC focuses more on mass balance equations, while the ADE is concerned more with the mass transport and fluid dynamics.
The advection-dispersion equation relies on concepts from differential calculus to describe the rate of change of contaminant concentration over time and space within a flowing fluid. It contains three components. First is the rate of change. The rate of change of contaminant concentration, which is represented by the one encircled, which is the partial derivative of C with respect to time. Second is advection. Advection is the bulk movement of contaminants by the flowing fluids with velocity. The rate of advection is proportional to the concentration gradient. The next component is dispersion. Dispersion describes the spreading of contaminant plume due to the molecular diffusion and mechanical dispersion. We can represent the combined effect of both types of dispersion using the second-order partial derivative of C with respect to x. Now, combining all the components from the previous slides will lead to this: the advection-dispersion equation in its general form for one-dimensional. Here is a sample problem that demonstrates the use of ADE. In our solution, the first step is to find the auxiliary equation of the given advection-dispersion equation. Thus, it becomes negative VE plus DE raised to 2 equals 0. Then we factor out E and solve for it, finding our first equation, which is C sub 1 e raised to 0 plus C sub 2 e raised to velocity divided by dispersion coefficients times x. Then, by applying the given and the boundary conditions, which is 1 milligram per liter at AB and 0 at groundwater level, we have our second equation, which is 1 equals to C sub 1 plus C sub 2. And our third equation, which is 0 equals C sub 1 plus C sub 2 e raised to 2 over 9. Solving using the second equation and the third, we have our C sub 1 and C sub 2. Then substituting the C sub 1 and C sub 2 in the first equation, we have the final answer, which is 1.236 times 10 raised to negative 4 milligrams per liter.
The advection-dispersion equation, also known as ADE, is extensively utilized in various practical contexts. In environmental engineering, it plays a pivotal role in modeling the transport of contaminants in groundwater, effectively simulating solute movement based on principles from fluid mechanics and mass transport theory across diverse environments. Additionally, ADE-based models assist in understanding groundwater flow in fractured aquifers with fractal characteristics, a task challenging with traditional approaches. By estimating parameters like hydraulic conductivity using field data, these models contribute to comprehending aquifer behavior. Lastly, the comparison between ADE and spatial fractional ADE in describing migration of non-reactive contaminants in homogeneous and heterogeneous soils underscores their importance in assessing risks associated with agricultural activities and devising strategies for sustainable soil.
As future engineers, we must continue to build around our surroundings without compromising our environment and resources. Let's remember our responsibility to apply our knowledge of topics in calculus to achieve a vision of tomorrow where we have clean and accessible water for everyone. Here are our references, and with that, we'd like to thank you for joining us in our underwater adventure. Thanks for listening, mateys!